Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 29 in our incredible new tutorial series where you're teaching your Raspberry Pi who's boss. What I'm going to need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent set of video tutorials. And in this class, we will be using the Sunfounder Raphael Raspberry Pi kit. Most of you guys probably already have your gear, but if you don't have your gear yet, look down in the description. There is a link over to Amazon where you can pick this kit up. And believe me, your life and my life will be easier if we are working on identical hardware. Sunfounder, putting the tech back in TopTechBoy.com. But enough of this shameless advertising. Let's talk about what I am going to teach you today. And what I'm going to teach you is I'm going to teach you about a new component in the Sunfounder kit, and that is the photoresistor. The photoresistor is a component whose resistance changes in response to the brightness of the light. So what I'm going to do is I'm going to jump in and I'm going to talk to you a little bit about the physics of how that component works, and then I'm going to show you a little bit about how to incorporate it into a circuit, and then we're going to build a circuit and program it up. So by the end of today's lesson, you'll be able to incorporate light detection, brightness into your projects. And so does that sound good? I hope it does. So I'm going to have to reconfigure here a second to get things up. Before I jump in and start building and programming, I want to show you how this photoresistor works. And so I've got to do a little tad bit of reconfiguration here, and I think I need to get out of your way. And then I need to switch over here and then switch over here. And then hopefully we'll have this sketchpad pop up here. Okay, there we go. That is looking pretty, good. Get that out of your way. Okay, so first of all, what is the photoresistor? We can look over here and you can see that I already have the circuit built up, but it is this little two-legged component, and you can see at the top of the two legs you have a little piece of glass, and then you have a little bit of a squiggly line, and that is the photoresistor. And what is the characteristic of the photoresistor? The characteristic of the photoresistor is its resistance changes in response to the brightness or the intensity of the light. The brighter the light, the lower the resistance of the component. The lower the light, the higher resistance of the component. So exactly how does this magic happen? I know some of you guys hate it when I go into the physics of these components, but I think the guys that really want to get into kind of looking under the hood and seeing how these devices work, they probably enjoy this. So how can you create a device whose resistance changes in response to the brightness of the light? Well, let me try to jump in and show you that you got to understand just a little bit of solid state physics. And so let me see if I can kind of jump in and show you that. And so let's just think of an atom, okay? And an atom has a nucleus, and so this is the nucleus here, we're going to say, and that has protons and neutrons in it. Now, orbiting around the nucleus are electrons, but the thing is that the electrons can only be at very specific energy states. So maybe we have an energy state here, and then we have this higher energy state, and then we have this higher energy state. The electrons have to be at a specific allowed energy state. So let's say that I have an electron right here. The electrons tend to fill up the lowest energy states first, and so the electrons can bounce around and go from one energy state to another, but their average value is always to fill the lowest energy states first. And so you can see that I've got an electron here. Let's say I had another electron here. So let's say that we had 2 electrons on this atom and they are in these 2 states here. Now, what if we have another atom over here? Well, if it's the same atom, let's say this is a gas and the atom is some distance away, this atom is not really interacting with this atom because they're far enough away. And so this can have its energy states as well. And then let's say that this one also has 2 electrons. Okay. Now, if these are in a gas, the gas is going to be an insulator because these electrons cannot go back and forth between the atoms because they're too far apart. So what do you have? You have no ability for electrons to move in response to a voltage. So you have what? You have an insulator. Now, the question is, what happens if we start bringing these atoms together? And instead of having a gas, let's say that we bring these atoms together and we bring them together in a very specific way to begin to form a crystal. So what I'm going to do is I'm going to start bringing this atom from over here. I'm going to start bringing it very, very close to this atom. Okay, and so now these atoms are together. Now what's going to happen? There is something in quantum mechanics called the Pauli exclusion principle, and that means that 2 electronic states cannot have the exact same quantum numbers, which means they can't have exactly the same energy level. So as we start pushing these atoms together, these two electrons are trying to occupy the same quantum state. So what happens? They have to kind of smear apart in order to satisfy the Pauli exclusion principle. So what's going to happen? This energy level is going to go up a little bit, let's say, and this energy level is going to go down a little bit, so they kind of move apart. And so as those atoms come together, instead of having exactly the same energy states, those energy states move apart a little bit, and then I've got 2 energy states instead of 1. Well, what is going to happen now if we start bringing a lot of atoms together and create a regular crystalline pattern like this, where we bring them together and we form a crystal? Well, each one of those energy states is going to begin to blur. It's going to begin to move a little up or move a little down. And now, instead of having discrete energy states, what you end up with is you end up with energy bands. You end up with these energy bands of allowed energy states. And it just so happens that you end up with something like this. So this is, on this axis, we have energy, and this is energy going up. And then within this band, you have all of these smeared out energy levels to where they basically just all come together and smear together, where you could have allowed energy levels anywhere from here to here. Okay, and those would be those energy states represented by those 2 electrons. Well, what about these energy states up here, which were empty? Well, even though they're empty, they're going to smear out as well. And so what you end up with up here is you end up with another smeared out energy band where you can have electrons. Now, as I mentioned over here, that the electrons always want to go to the lowest state. And so where are the electrons going to go? They're going to go down to this band down here, and they're basically going to fill up. All of the electrons are going to fill up all of the allowed energy states down here in this lower band, like this. Okay, so I've got all of these electrons down here, like this. Now up here, I've got allowed spots for electrons, but they're empty. Okay, I've got allowed spots for electrons, but they're empty. So this band down here is called the valence band. This is where all your electrons are, the valence band. And this band up here is called the conduction band. So kind of in an oversimplified way, in a crystalline material, in a semiconducting material, the valence band is down here, it's all full, the conduction band is up here, and it is all empty. Now we have to ask, for this configuration, if we took a voltage and applied a voltage across it, what would happen? Well, what would happen is that you would get no conduction at all. It would act like an insulator. Well, you say, what about all of these electrons here? Well, the thing is, what you've got to think about down here is you have to think of the valence band as a room, and it's a room full of people, and the people are packed in from front to back, side to side. The room is completely filled. Now imagine you're in the corner and you're told to walk to the other corner. You can't walk from one place to the other. Why? Because the room is full of people. So there is no conduction happening down here in the valence band. Well, how about in the conduction band? The problem there is the room is completely empty, and so there's no one available to walk across the room. So what happens? The material sits there, and it is an insulator. All right, but now this is where the magic happens, that if you have a photon is a little discrete package of light. It's sort of like one little discrete package of light. You could think of it as like a little marble of light. And as that comes in, as you have your photon come in and strike your material, what it does is it is absorbed, but the energy of the photon has to go somewhere. And where the energy of the photon goes is one of the electrons it picks out, and that electron will be kicked up to the conduction band. And so we are going to be left with a hole down here. Let's see. Ooh, that was too much. Let me see. My eraser was too big. Okay, we're going to be left with a hole down here. And let me go back and put the hole in. Okay, we're left with a hole down here. And then that electron comes up here. Now, the way you could think of it is, in that upper room, you have one person, and he can walk across the room. What are you doing? You are conducting now. You're getting some conduction. And also, if you think about it, this hole that's left behind here, that allows a little conduction down in the valence band as well, because a person could kind of wiggle that hole around and could move from one corner of the room or one end of the room to the other. And so you are getting conduction in both the conduction band and the valence band as this electron is up here. Well, if there was one photon, there's going to be one electron. You're going to get a little of conduction. But if I have 10 times as many photons, I'm going to get what? 10 times as many electrons, and I'm going to get more conduction, and the resistance is going to go down. So the resistance of a semiconductor material like this, the resistance is going to go down as the light intensity goes up, because there are more photons coming in. Those photons are kicking more electrons up to the conduction band, allowing the conduction band to conduct, and those holes left behind down in the valence band are able to conduct as well. So what do we get? We get something where the resistance is proportional to the amount of light. Now, is that pretty neat, or did I just lose 3/4 of the audience? Usually there's no in-between on this. When I start talking about physics, there's going to be some people that love it, and there's going to be some people that hate it. But now let's go in and let's say, what do we have now? We have a resistor. We have a resistor, and that resistor has a resistance that depends on light, the amount of light. And as the photons are coming in, the more photons coming in, the more the resistance drops. And so how would we use that in a circuit? Well, what we need to do is we need to create a voltage divider. So let me clear this again. Let's create a voltage divider. So what I'm going to do is I'm going to come in and I'm going to get Vs is going to be equal to 5 volts, and I'm going to get that off of the Raspberry Pi, and then I'm going to come down and I'm going to put that through my R. I'll call this R, what will I call this? P for photoresistor. Okay, and that I'd like to just kind of put a little arrow like that indicating that the resistance is going to depend on the number of photons. And then we're going to put down below that another resistor to create a resistor divider. And this will just be a standard resistor, so we'll just call it RL. And then what we're going to do is we are going to measure the V out here. Okay, and so this would go to a GPIO pin on the Raspberry Pi. So how does this work? Well, we know that voltage is equal to current times resistance. And so here, if I divide both sides by voltage, I could say that current is equal to the voltage divided by the resistance. And for a series circuit, the resistance is the total resistance. So I can say the current is going to be equal to the voltage, which we said is Vs, and then it's going to be divided by the total resistance, which is Rp plus RL, the photoresistor resistance and the load resistor resistance. Now, what is V out going to be? V out is going to be that current times RL, and that current is Vs over Rp plus RL times RL. Okay, now RL doesn't change, Vs doesn't change, so what does V out depend on? V out depends on the resistance of the photoresistor. Now, if the light comes on, that resistance is going to what? The resistance is going to go up. When the light comes on, the resistance is going to go down. And when the resistance goes down, this numerator is getting smaller. So what does the overall current do? It goes up. And then what is V out going to do? It's going to go up too. So when you hook things up like this, the brighter the light, the higher the voltage that you are going to measure at V out. Does that make sense? I hope it does. So you can see we can go from solid state physics to kind of an energy diagram of what's going on inside of our component, and then we can take that behavior, we can create a voltage divider here schematically, but now what we need to do is we need to go in and build that circuit. If any of you guys are still out there listening, I hope so. So let's switch over and let me do a little bit of switching to a different view here. I need to do a little bit of Windows management here. So let's see, I'll come and I will switch over to this view. And now what we have is we have a schematic. We have a schematic of what I need you to build. And then besides the schematic, what we have is we have a live shot of the circuit. Now, a little bit about what we have here. We're using, to do this, to measure V out, what we need to do is we need to measure an analog. We need an analog in, and you know that the Raspberry Pi doesn't have an analog in, so we are using the most excellent ADC0834 from the SunFounder kit. And guys, we're doing so much analog in, I just always leave one of these ADC0834s on a breadboard hooked up, and that way when I need to do analog in, I don't have to come and build all of this part. And so hopefully you guys already have one of these and have this part hooked up, and all you're going to have to do then is come in and put in the photoresistor, and you can see that I have it in a voltage divider. And so let's look here and see. Let me see if I can show you this carefully. So the left leg of the photodetector I have coming down through this red wire down to +5 volts. So the +5 volts goes to the left leg of the photoresistor. The right leg of the photoresistor is connected to a 10,000 ohm resistor. Now, why 10,000 ohms? Because when you create a voltage divider and you want good sensitivity, you want the value of the load resistor to be about the average value of the photoresistor. And so the photoresistor is probably somewhere nominally between 5,000 ohms and 15,000 ohms, depending on the light. And so a good load resistor would be about 10,000 ohms. So we've got a 10,000 ohm resistor. It's in series with the photodetector, and then the right leg of the load resistor is connected to ground. Now, where the right leg of the load resistor is hooked to ground, the right leg of the photodetector is hooked to the left leg of the load resistor, and then that node, I have a wire coming over to channel 0 of my ADC0834. So if I've just totally lost you, what you can do is you can come over to www.toptechboy.com and you can search on something like using a photoresistor to detect light on the Raspberry Pi, and then you can get your own version of the schematic, which you can click on and then get a much bigger view on. Okay, but I think most of you guys that are following along in these lessons would be able to hook this up now just by my description. And then here is just again kind of a view of what this thing looks like. You can see that the photoresistor has that little squiggly on it, and that squiggly is creating a long path to pick up photons, which is, basically just trying to make it more sensitive. So that circuit is hooked up. So we should be ready to code now if I'm thinking about this right. So what I'm going to do is I'm going to come over here and I am going to show you my my Raspberry Pi view, and what you can see is I have Thony already fired up, and so we are just going to need to write some code here and then see if we can detect some photons. All right, so this is actually going to be a pretty easy program to write, I believe. Let's see if I can do this without making massive mistakes. Okay, I need to come up and I need to create a new program, and let's go ahead and save as let's call it photon detect.py, and the .py is pretty important, and boom, there we are. All right, we're going to be using those GPIO pins, so I'm going to say import rpi.gpio as GPIO. Then we're going to be using the ADC0834, so I'm going to import ADC0834 like that. And now I'm going to import the sleep library, the time library, because I'm going to want to put some delays in there. So I'm going to say from time import sleep. Now, why do I want to do it that way? Now I can just do like sleep point 1, sleep point 2. I don't have to keep putting time.sleep. I can just say from time import the library sleep, and that should work. Now I need to tell it that I am using the set mode. I will be using the most excellent GPIO.BCM numbering scheme. Why am I using the BCM numbering scheme? The reason I'm doing that is because I'm using that breakout board, from the Sunfounder kit, and that breakout board is numbered in the BCM numbering scheme. So if I do that, then I can just read the pin numbers right off of that breakout board. Okay, now I need to go ahead and set up the ADC0834. So I do ADC0834, and then I'm going to do a set mode, and what I'm going to do GPIO this is just a set up like that, and I don't have to give it any parameters. It's as simple as that. ADC0834.setup, that's just telling it to fire up and start. Now I'm going to do a try, and then if I do a try, I'm going to do the accept, and I need to do the accept here. Accept. And what does that mean? It's going to stay up in the try until it sees something, and then it will jump down to the accept. And so when do I want to accept out? On keyboard interrupt like that. And then what do I want to do on the accept? I want to give it a second to rest. So I'll just say sleep, and I'll sleep for 0.1 just so it can finish up whatever it's doing. Then I'm going to do a GPIO dot clean up. We always want to clean up our mess for the next guy. And then I'm going to print that I've gotten down here just by saying GPIO good to go, like that. All right, now I've got my accept. What are we going to do up here in the try? Well, I want to stay in the try, so I'll say while true. When is true true? True is always true. So it'll just loop here until it sees the control C or the keyboard interrupt, and then it'll jump down to the accept. And so what do I want to do here? I want to read the light val. And then how do I read the light val? That is equal to ADC0834, which is the object we created, dot get result singular, and I am reading off of channel 0. And how do I know that it's channel 0? Because this photo detector, at this connection between the photo detector and the resistor, I ran a wire over to the channel 0, okay? And so then since I'm connected to channel 0, I need to read from channel 0. So we'll come over here, and then I will close that parenthesis out like that. So now I should at this point have light val. And so now let's just print light value, like that. And then I need to give it a value, so I'll say print light val, like that. Okay. Now I will do a sleep for let's say 0.2 seconds. Could it really be that easy? I ask you, could it really be that easy? Okay, so now let's see if there's a way, if there's any view here that might be interesting for you. I'm trying to see if I can show you the circuit and the code at the same time. There, I believe we can. So I'm going to bring this on over here now like this, so you can see the photoresistor from above on my circuit. And then over here, you can see what the code is doing. So that looks pretty good. Man, how many mistakes did I make? Last couple of times I made a lot of typos, and so I am almost afraid to even have you hold your breath because there's probably so many. But I will ask you to hold your breath and let's see what happens. Am I getting values? Look at that. Boom. Okay, so I'm reading a 202 in bright light. Okay, so remember, the brighter the light, the lower the resistance, and the lower the resistance, the greater the current, and the greater the current, the greater the value that you're going to read. So in bright light, I should be getting a high number. And this ADC0834 reads from 0 to 255. So you can see here in bright room light, I am getting 202, so that seems pretty good. And so now let's see what happens if I begin to shade the device and bring a little shade. Do you see how it went down? And then it's going down, 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 down. And the darker I make it, and of course I can't make it completely dark, but you see how we went from 200 all the way down to 16? Look at that. That is pretty good. And do you see how it's doing it smoothly? Why? Why is this doing this? Because my hand is blocking the what? The photons. Fewer photons are hitting the surface of the sensor. Fewer electron hole pairs are being generated. The resistance is higher. When the resistance is higher, the current is lower and the red value is lower. And look at that. Now let's see if we can get more even by using a flashlight. And if I just really look at that 230, if I get it right up there, I'm up to 235. I've probably almost saturated it now, all the way up to 230 is about the highest that I can get. And then just sitting with my hand, it looks like I can get down to maybe in the teens, maybe 15 or 16 is a low value as I do that. Okay, guys, boom. That is pretty neat. Now, this has been a pretty easy lesson, but this photo detector is actually a very sensitive and I consider a very important component And what it allows us to do is it allows us to know, like maybe if you're in a greenhouse, you could detect how much sunlight you're getting by looking at the brightness in the greenhouse, like how many hours of bright light are you getting in a greenhouse. Or maybe in your home you could detect, if the room's dark, maybe you would want to turn the lights on. You see, there's some interesting things that you could do. Like one thing that you could do is you could think about something like, if the room is dark and there's a person in the room, then what you could do is you could turn the lights on. Okay, and then if the person left, then what you could do is you could turn the lights off. You see, you could do something like that. But I think for your homework, what I'm going to do is, you guys remember that we had that PIR detector, that person motion detector. It looks for motion and heat. And so this is what your assignment is going to be. What your homework assignment is going to be is to create a device that will sound an alarm if your room is dark and there's someone walking around in it. Now, why do I do that combination? Because during the day, I'm not surprised if there is someone walking through the house. Why? Because that's what people do in their houses. They walk around through their houses. But at night, you turn your lights off, you go to bed, you don't want someone walking around in the dark. So I want you to create an alarm that goes off if it sees a person walking around in a dark room. It will alarm. So a little bit of kind of like a security device. Does that make sense? I hope it does. Okay, guys. Oh, look, we got the fisherman out there. Okay. I hope you're having as much fun taking these lessons as I am making the lessons. Next week, I'll show you my solution to the homework assignments. And you guys start doing your homework again. As we've gotten more and further along, there's fewer and fewer of you guys posting homework solutions. I think that you guys are just starting to kind of slag off a little bit and watch the videos and not doing the projects. These projects, even if you're familiar with the material, it's really good practice, and it's really good for building your skills. If you like the video, be sure to give us a thumbs up. If you haven't already, subscribe to the channel. And as always, share this with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.